Greetings everyone, and let's continue with our course. So last class we were solving few numericals. Let's continue with our numericals. Let's take another simple problem wherein let's find out, this is an example, find out the hydrogen produced from, let's say, 1 kg of water. Okay. So we know that water, when it is electrolyzed, it gives hydrogen and half mole of oxygen. So as we can understand, this is 1 mole of water gets us 1 mole of hydrogen and half mole of oxygen. So let me write this down. So that implies 1 mole of water generates 1 mole of hydrogen and half mole of oxygen. So we have been given 1 kg of water, so that means 1000 grams, and 1 mole of, we know it is 1 mole of water is nothing but 18 grams. So let's find out the how much moles of water are there in 1 kg of water. So number of moles of water in 1 kg, that is 1000 grams, is nothing but, let's just divide it by 18. So that comes somewhere around 55.55 moles. So that, what does it imply? It implies that 1 kg, if 1 mole of water is going to get us 1 mole of hydrogen, so 55.5 moles of water are going to get us 55.55 moles of hydrogen and exactly half mole of oxygen as well. So, and we know, let's also find out the mass of hydrogen produced. So we can find out, as we have to first of all convert the molar mass of hydrogen. So let's find out mass of hydrogen produced is nothing but moles of hydrogen produced into its molar mass, which is constant, 2 molar mass of hydrogen. So this is 55.5 times 2, that gives close to 111 gram of hydrogen that will be produced from 1 kg of water, that is 1000 grams of water. So there is it's a complete mass balance. There is no materials that are coming into picture. No matter what materials we will use, no matter what temperature will be operating the electrolyzer at, if we supply 1 kg of water, it will produce roughly 110 grams of hydrogen. Of course, the energy that is required by the electrolyzer will vary upon the materials. It will be decided by what materials we choose, what catalyst we choose, what is the electrolyte, and so on and so forth. So let's move on. Let's move on to the another example wherein we have hydrogen and oxygen fuel cell, which is operating at the temperature, operating temperature is, let's say, 80 degrees Celsius, and the operating pressures of hydrogen is, let's say, 3 atmosphere, and air is being supplied instead of oxygen. Air is supplied at 5 atmosphere. So this becomes pressure of hydrogen, this becomes pressure of air, and as we have just found out in the last class, E naught, that is reversible cell potential, is 1.23 volt. So we have to find out the Nernst potential nurse potential at these operating temperatures and pressures. So, we need to find this up. Let me write this on this side. En is to be found out. So, let us use the enthalpies and entropies. So, this for hydrogen it is, and oxygen is 1, and then this is minus 286, this is all in kilojoules per mole if it is on molar basis, and entropy is, let me confirm this, yeah, it is 130.68, then this is 205.14, and this is 69.91, this is all in, sorry, joules per mole per Kelvin. Okay. So, we need to find out the nurse potential, and this Cp, as we know Cp depends on the temperature as well. So, we need to integrate all those equations, we have to find out the entropy change, and then we need to use the nurse potential equation to find out the final value. So, let us first write down the equations. So, here En, or it is, I can also write it as at different pressures and temperatures, it is nothing but Et minus RT by Nf ln of activity of water divided by partial pressure of hydrogen times partial pressure of oxygen raised to half. So, this is my equation 1. What is my Et? Et is nothing but E naught plus entropy change of that reaction times the temperature difference, that is T minus T naught, that means it is 80 degrees minus 25 degrees. And what is your, let us call this as equation 2, and this entropy is nothing but entropy change plus integration of heat capacity as a function of temperature divided by temperature times dt. So, this varies from over T naught to T. Let us call these equations 3. So, our first step is to find out the entropy change, and then we move to equation 2, and then finally to equation 1. So, let us find out the heat capacities. So, let us first write down the equations. So, Cp of H2 is, as we know, it is 56.506 plus 22,222.6 times T to the power minus 0.75 plus 116500 by T minus 560,700 times T to the power minus 1.5. What is our Cp of oxygen? It is 37.432 plus 2.0102 into 10 to the power minus 5 times T to the power plus 1.5, T to the power 1.5 minus 1.7857 times T to the power minus 1.5 and plus 2368800 T times T to the power minus 2, and Cp of water is 143.05 minus 58.004 times T to the power 0.25 plus 8.2751 times T to the power half minus 0.03698 times T, right. So, we have written these equations as we have discussed this before as well. Let us first find out the entropy change of every species, and then let us find out the entropy change of the entire reaction. So, let us also write this as entropy change of the reaction is, entropy of the products minus entropy change of the reactant. So, this is where we have to get finally. So let us first find out the entropy change of the hydrogen. So entropy of hydrogen as entropy of hydrogen at STP, which is given, plus this entire equation has to be integrated, integration of T naught to T. T naught is, let us say, 298, and this was 2, and that is 80 degrees. So 253, 353 integration. Let me write this up as 56.506 minus 22.6 to the power t to the power minus 0.75 plus 116500 over t minus 560700 t to the power minus 1.5. So this is the entire heat capacity. So let me put this up, and this is whole divided by T dt. So this is our expression, and entropy change is given as 130.68. It is at STP. So let us solve this expression. 298, 353. So 56.506 divided by T minus 222.6 times T to the power minus 1.75 plus 116500 divided by T square minus 560700 times T to the power minus 2.5, right. So this whole thing is to be, okay, let us use the next slide. So that equals 130.68 plus, let us solve the integration. So it is 56.506 ln of t minus 2222.6 times t to the power minus 0.75 divided by minus 0.75 and plus 116500 times t to the power minus 1 divided by minus 1 and plus 560700 times t to the power minus 1.5 divided by minus 1.5. This whole thing is to be integrated from 298 to 353. So if we solve this up, this comes 130.68 plus 9.57067 minus 49.280 plus 60.911 minus 16.302. So let me again simplify this. It is 130.068 plus 4.899. So it is ultimately 135.579. This is joules per mole per Kelvin. This is entropy of hydrogen. Yeah, it is entropy of hydrogen. So we have first solved the entropy of hydrogen, which is one of the reactant species. Let us move on and find out entropy of oxygen, which is, write entropy at STP of O2 plus integration of again Cp as function of temperature by T. This is 298 to 353 dt. So entropy at STP of our oxygen is 205.14 plus, let us include the Cp term, which is 37.432 plus 2.0102 times 10 to the power minus 5 times t to the power 1.5 minus 1.78570 t to the power minus 1.5 plus 2368800 times t to the power minus 2. This is whole divided by t dt 298 to 353. Let's move on to next slide. This is 205.14. So this is at plus 298 to 353. So this is 37.432 ln of t plus 2.0102 into 10 to the power minus 5 t raised to 1.5 by 1.5 minus 1.78570 times t to the power minus 1.5 by minus 1.5 plus 2368800 times t to the power minus 2 by minus 2. So if we solve this up, so that comes 205.14 plus 6.34 plus 0.019941 minus 0.00051957 plus 3.8323. So this becomes 215.332. This is entropy of oxygen, joules per mole per Kelvin. So let's again go ahead and write it for entropy of water, which is entropy of water at STP plus integration of Cp T dt dt. This is at 298 by 353. So if we again we have to integrate this, and then we have to solve this at for different Cp values, like as it is a function of the temperature. So let's substitute 69.91 plus integration of 298 to 353. So Cp is basically 143.05 minus 58.04 times t to the power 0.25 plus 8.2751 times t to the power half minus 0.03689 times t whole divided by t dt. Let's go ahead. So that becomes 69.91 plus integration of 298 to 353 143.05 by t minus 58.04 t to the power plus 0.75 plus 8.2751 t to the power minus 0.5 minus 0.03689. So if we solve this up, it comes 69.91 plus 5.722. So that comes close to 75.632 joules per mole per Kelvin. So this is entropy of water. So once we solve this up, so let us find out the entropy of the entire reactions. Now that we know the entropies of individual species. So what is our reaction? Let me write that reaction one more time. H2 plus half O2, that gives H2O. So entropy of the reaction is entropy of products minus entropy of the reactants. So entropy of product is basically water, that is 75.632 minus entropy of hydrogen, that is 135.579, and plus half of entropy of oxygen is 215.332, right. So if we solve this up, that comes close to minus 167.604 joules per mole per Kelvin. So this is my entropy of the reaction. Please note this is not at STP, because now since we have deviated from STP, the entropy will be different. Now once we found out the entropy change of the reaction at operating temperature, let us find out as per equation number 2, what is our ET? ET is E naught plus entropy change by NF T minus T naught. So E naught, as we all know, it is a standard number, it is 1.23 volt in case of fuel cell, plus entropy change is negative minus 167.604 joules per mole per Kelvin divided by 2 times 96,485, and this is 80 minus 25. So this comes close to 1.18 volt. So this is my ET. Once we know the ET, let us move ahead and find out the Nernst potential at different operating temperature and pressure. So we know En, which is also, I can term it as a different pressure and temperature as ET minus RT by NF ln of activity of water divided by partial pressures of hydrogen times partial pressure of oxygen raised to half. So if we remember, or let me write this down here, partial pressure is a pure hydrogen that we have supplied at 3 atmospheres. So that becomes the partial pressure, that is the complete activity of the hydrogen, whereas we have supplied air at 5 atmospheres, right. So partial pressure of oxygen, which is partial pressure of air, that is pressure of air times 0.21, that is the 21% oxygen is there in air. So we need to find out the partial pressure of the oxygen. So that means we need to multiply 0.21 to the pressure of air. So that is our at 5 atmosphere times 0.21. So that comes close to 1.05. So this is our pressure of oxygen. So let us go ahead. We have ET equals 1.18 volt. Let us bring those numbers, that is our calculations in the final equation, En times ET minus RT by NF ln of activity of water, which is 1, times pressure of hydrogen times pressure of oxygen raised to half. So ET is our 1.18 volt minus 8.314 into operating temperature is 353 divided by 2 times 96,485. Now activity of water is 1 and partial pressure of hydrogen is 3 atmosphere. It is a complete and pure hydrogen. So what is our activity of oxygen? It is 1.05, that is pressure of oxygen raised to half. So if we solve this up, this comes close to 1.20 volt. So this becomes our En, that is Nernst potential. So in other words, so this is for H2 air fuel cell having pressure of hydrogen as 3 atmospheres or 3 bar also we can say, and pressure of oxygen as 5 atmosphere. that will have the cell potential of roughly 1.2 volt. So that is the meaning of having nurse potential. So that what it implies is, if we are operating a pressure fuel cell or even the electrolyzer at different temperatures and pressure conditions, we, or particularly in fuel cell, let me say, if it is operating at, let us say, 3 and 5 atmospheres of hydrogen and air respectively, we can expect the pressure, the nurse potential to be somewhere around 1.2 volt. So this is very important to understand, that even if we increase the pressure of hydrogen as well as oxygen, or even if we supply oxygen and raise its pressure, En is not going to increase very linearly. That is primarily because of the logarithmic term that we have, which connects the pressure terms with the potential. So this is what the nurse potential that we can find out. We can also find out the nurse potential for the reverse reaction, that is electrolysis reaction involving hydrogen generation as well as oxygen generation when we supply water. And if it is, let us say, operating at the same parameters, that is, let us say 80 degrees and 3 atmosphere and 5 atmospheres, we can also expect the nurse potential of the electrolysis somewhere close to 1.2 volt. But in that case, it will be a negative term, signifying the fact that the potential has to be supplied, the energy has to be supplied to basically evolve those gases in the reaction, during the reaction. So with that, we will stop here, and we will take on with the characteristic curve, the different losses that are involved in a typical fuel cell device, and then we will have a closer look at individual losses as well as the reversible and as irreversible losses separately as when we proceed. With that, thank you all.